This lecture discusses the three environmental impacts associated with refrigeration. These include the CO2 emissions associated with its energy use, the stratospheric ozone depletion that takes place because of the Freon and CFC refrigerant, and also the greenhouse gas emissions from these synthetic refrigerants as well. But first, let's talk about the refrigeration process. The first prototype of vapor compression refrigerator was invented in 1842 by an American physician named John Gorey, who built a working prototype that did not work. It was a commercial failure, but it really set up the principle for how modern refrigeration works. Refrigeration is fascinating. It relies on the physical properties of a refrigerant to absorb and reject heat energy as it is expanded into a gaseous state and compressed into a liquid state. Let me go over the different stages. The coolant or refrigerant is in a liquid form as it enters into the expansion valve right here. As it passes through, the sudden drop in pressure makes it expand, cool, and turn into a gas. As the coolant flows through the evaporator tubing, it absorbs and removes heat from inside the chiller case or refrigerator. Then the compressor squeezes the coolant, raising its temperature and pressure. It's now a hot, high-pressure gas. As the refrigerant flows through the condenser, it cools, rejecting heat, including the heat it previously absorbed. When it is finally cooled, it turns back into its liquid state, and the refrigeration cycle begins again. So looking at energy usage, you should know that refrigeration is highly energy intensive, and it usually takes either, in this case, 55% of a store's energy usage. Sometimes I've seen this number down around the high 30s, but no matter what, refrigeration is definitely an area where any store can save money through efficiency efforts. Similarly, if you were to look at the cost of a chiller, the vast majority of the expenditures goes to the electricity used for the chiller. Much less energy is spent on the first cost of the chiller itself or the refrigerants that are used to recharge it. Because of their energy profiles, most retail stores and food manufacturers have a program for updating their refrigeration systems. And same thing with utilities that offer rebates and other sort of incentives to upgrade refrigeration systems. The second environmental impact has to do with the chlorofluorocarbons and their impact in the ozone hole. The synthetic form of chlorofluorocarbons was really invented at the end of the 1920s, and it was considered a great advancement because it was replacing a lot of refrigerants that were toxic and flammable and explosive, such as ammonia and propane and sulfur dioxide. So Thomas Midgley is a scientist at General Motors who leads a team that invents Freon. And Freon is considered a miracle. It's colorless, it's odorless, it's not flammable, it doesn't appear to be toxic at all, and it quickly takes over the refrigerant market. Of course, it wasn't until the 1970s that people began to realize that chlorofluorocarbons had other environmental damaging impacts. This list here includes some of the key dates. 1974, the links between CFCs and ozone depletion are first made. By 1987, the Montreal Protocol is put in place, and it bans and phases out the CFCs and introduces HCFCs, which is considered a better alternative. By the 1990s, people are beginning to look at HCFCs in a different way and realizing that not only is it very successful in terms of replacing CFCs, but by the end of the 1990s, people are wondering about its own greenhouse gas potential. Just recently, in 2016, an international agreement was completed that limited the use of hydrofluorocarbons, and this was added as an amendment to the Montreal Protocol. And one of its outcomes is to ban the remaining HCFCs by 2020 with a 99.5% reduction rate. I think it's really important to understand how ozone is degraded in the upper atmosphere by the chlorine molecules that emanate from CFCs. The way the process works is that chlorine, which is highly reactive, combines with the ozone molecule, which is actually 3 oxygen atoms. By pulling off one of the oxygen atoms and creating chlorine monoxide, some oxygen is created, just O2. And that chlorine monoxide moves along until it meets another chlorine monoxide and forms a chlorine peroxide. The compound, this molecule, is easily broken apart by sunlight, creating chlorine atoms again and another oxygen molecule. So what happens is that this is really a catalytic process that just continues on and continues on. And that's the thing I think that's most important to know about chlorine in the upper atmosphere, is that it doesn't go away quickly. Of course, the outcome of this catalytic process is the ozone hole over Antarctica, which is 9.3 million square miles. And as a point of comparison, the United States is 3.1 million square miles. Fortunately, due to the Montreal Protocol, this ozone hole is actually reducing in size. So let's move over now to discuss the topic of HCFCs and global warming potential. When CFCs were first being replaced by HCFCs, the idea seemed really great. So here is the CFCs that needs to get replaced. It's the R12, and the R22 and R142B were considered really good replacements. And if you look at it, the ozone depletion potential goes from 1 down to 0.055 and 0.065. So that makes a lot of sense. But if we drop down one more row, we can look at the global warming potential, and we can see that the difference is not as significant. So for CFCs, the global warming potential is a whopping 2,400. For HCFC, it's about 1,800. And for the HCFC for the 142B, it's even higher, really close to the original CFC. On the plus side, when you looked at CFCs, it had a life cycle of about 120 years, and both the HCFCs are at 12 and 17.9, so significantly less, but still enough to be concerned, and that's why these are also being phased out. These HCFCs are being phased out. To help with the phase out of harmful refrigerants, EPA has created the Green Chill program, which is by far the best known program in the country for this type of work. And as with many voluntary programs, it is based on a combination of measurement that partners get involved in, with technical assistance, and with a recognition program. So the measurement includes calculators and benchmarking and tracking tools that are on the website. And the technical assistance includes a webinar series and online guides and tools. And then there is also a annual awards program, as well as a store certification effort that can take place. EPA also maintains something called the Significant New Alternatives Policy, which is like a database or an evolving list of alternatives for refrigerants based on environmental and human health impacts, as well as the current knowledge about available substitutes. And so the criteria that's being used to look at good substitutes include its ozone depleting potential and global warming potential, toxicity, flammability, any kind of occupational or consumer health and safety issues, local air quality, and ecosystem effects. So this is the go-to database for finding alternatives for refrigerants. So I'd like to end with this amazing chart that shows the trade-off between the high and low ozone depleting substances, as well as substances that have high global warming potential, and then also those other natural refrigerants that have a whole other host of concerns. So if we look on the right-hand side of this slide, you can see the concerns from ozone depleting potential. That green circle, the red circle has, or stop sign, has a global warming potential. There's a symbol for flammability, another symbol for slightly flammable materials. The light bulb questions the efficiency of the refrigerant. The dollar sign shows the cost, and of course the unhappy face shows toxicity. Never seen that one before. So you can see that while the original CFCs did really well in terms of their efficiency, their cost, their lack of health concerns and flammability, at the bottom of the table, you can see a bunch of alternative refrigerants with a host of concerns. So we're actually returning back to some of the refrigerants that we thought we got rid of back in the 1930s. So, for example, propane, it's expensive, it's highly flammable. Ammonia, highly toxic and flammable. And CO2, which is being used as a very interesting refrigerant, I think with more and more success, is considered highly costly and not very efficient in terms of in terms of acting as a refrigerant. Anyway, by looking at this chart, you can really see where the trade-offs are. And we're really moving into a world of imperfect solutions, but I think that the technology is moving forward quickly, and more grocery stores I know are beginning to adopt the CO2 refrigerant.